Hey class, let's look into chapter 3. So we're going to get into probability. And to start things off, let's try a little experiment. So suppose we have a fair six-sided die and we're going to roll it 30 times. So we'll do that here in a moment virtually. What do you think would happen? So before doing the experiment, you could write down what you would expect to occur. If you want to pause and think about it, you can. But honestly, what we would probably expect is, if it's a fair die, to have the same amount of outcomes for each face. And if you're unfamiliar with dice, it's a cube that has 6 sides, and the sides look like this right here, right? And those represent the numbers 1, 2, 3, 4, 5, 6. Okay, so we would expect to have the same number of outcomes for each of the 6 sides. And since there's 6 sides and we're going to roll it 30 times, we would go 30 divided by 6. We'd probably expect to see 5 of each. Now, are we going to see that in an actual experiment if we only roll it 30 times? Most likely not, but you might, or it'll be close, right? So I did already start the experiment to give ourselves a head start, and I did that in StatCrunch. So in StatCrunch, you can actually go to, let's see, let's close that. If you're on a main StatCrunch page, if you click on applets, right, the applet menu, you'll see an experiment, and one of those is roll die, right? So right there, you can see that there's a roll die, and then that'll shake to roll dice, okay? And then you can roll a die a bunch of times. Right? Even has a little sound effect, okay? But I already did 24 of them to get things going. So let's finish this off. I'm gonna roll it 6 more times to get to 30. A 4, a 4, a 6, a 2, another 2, and a 4, okay? 3 more 4s, and a 6 and 2 2s. Great, so let's record the data and see what we got. So if you wanted to pause and record it on your own, looking at this screen, that would be fine. Or you can fast forward, because I'm going to do it right now. So if I go back to my screen, here's what I ended up with. I had a tally of 5 ones, so the frequency on that one was 5. 2s came up quite a bit on my experiment. 3s, I had 4 of them. 4s, I had 7. 5s, I only had 3, and 6s, I only had 3. So who knows if that applet has fair outcomes, right? So those would be the frequencies. Let's see, does that all add up to 30? Did I do it right? I think so. Okay. Now, what about relative frequency? What would that be? Well, relative frequency just tells you to take the frequency and divide by the total frequency, right? So that would be about 167, right? So if I fill those in, rounding to 3 decimal places, you would see something like this. Let's see, I need to get a calculator. And so 7 divided by 30. And then 3 divided by 30. So as we can see, we're a little bit off of what we would expect. Right? We expected to get 5 of each. Only one of them had 5, right? 0.167. But they're all pretty much varying around that. And we only did it 30 times. Now, so do the results fit our expectation? Somewhat, maybe even not really for this one. Now, instead of rolling the die 30 times, suppose we did it 3,000 times. What would you expect to see? Well, then we would probably expect to see 3,000 divided by 6, 500 of each, right? And there we would probably be a little bit closer to the 500, or close to that percentage of 16% per outcome, right? And that's what's called the law of large numbers. So as an experiment is repeated over and over, the empirical probability of an event approaches the theoretical actual probability. So we have empirical, that just means we're actually doing the experiment. Theoretical is basically what we expect, which is actually the actual probability of what should occur, right? So with probability, then you can predict outcomes. Okay, so let's look at some detailed information about probability and then follow it up with some examples. Some common probability vocabulary. We'll use terms like probability and experiment, which is an action or trial, and outcomes are recorded, right? So an example could be a probability experiment consists of rolling a fair six-sided die, just like we did. For outcomes, the result of a single trial and a probability experiment. So the outcome of a first roll might be 3. Okay, that would be an outcome. So it's a single trial. The sample space is the set of all possible outcomes. So all possible outcomes is your sample space. And notice how we write it. So there's, every time I roll a die, I'm going to get one of those 6 things. 1, 2, 3, 4, 5, or 6. So that's called the sample space. Now an event consists of one or more outcomes and is a subset of the sample space. And the events usually that comes with the question, the probability question, right? For example, what is the probability of the event rolling a 3? That would be an example of an event, right? Or maybe rolling an even number, or rolling a number less than 4. Those would all be examples of events, comes in the question. Finally, a simple event is one that consists of just a single outcome. So the event roll a 3 is a simple event because there's only one way to roll a 3. Rolling an even number is not simple because you can get an even number 3 ways, 2, 4, or 6. So simple, there's only one way to get it. And that brings us finally to our formula, which we'll be then experimenting with here. So anytime you want to calculate a probability, and this is what's called theoretical probability, we take the number of outcomes in the event E and divide by the total number of outcomes in the sample space. So actually it's a lot like finding relative frequency. I'm just kind of calling it something different now, calling it the probability of an event occurring. Okay. So let's look at some examples. How about if we try to find the probability of rolling a 3, right? So we're going to roll a 6-sided die. Right? What's the probability that we get a 3? Okay. And for each of these, we're going to write as a reduced fraction, a decimal rounded to 3 decimal places, and a percent rounded to 1 decimal place. So, and I'll use a little notation here. So what I'm going to do is write this. This is notation for that question. Find the probability of rolling a 3. Okay. And so again, it's this fraction using this formula. How many ways are there to roll a 3? In that sample space, there's just one because there's only one 3. And there are 6 values in the sample space. So the probability is 1 over 6, which as a decimal is 1.67, and as a percent to 1 decimal place, I would just move that decimal over 2 places to convert it to a percent, or multiply by 100, 16.7%. So we expect to see a 3 16.7% of the times that we roll the die. What's the probability of rolling an even number? So we can say probability of even. So whatever's inside that parentheses is just descriptive of the event. So the bottom number we know is 6 again, because that's the number of outcomes in the sample space, total possible outcomes. And how many ways are there to roll an even number? Well, you can get a 2, you can get a 4, or you can get a 6. So there are 3 of them. So that would be 3 out of 6. That reduces to a half. As a decimal, 0.5. Move the decimal over, or 100 multiplied by 150%. So half of the time you would expect to roll an even number. Makes sense because half of the numbers are even. Let's see, is the event in part B a simple event? No. Why? Because the top number is not 1, right? Like this number here is not a 1. There are 3 ways to get an event. Part A, that's simple, right? Part B, not simple. So a simple event has to have that numerator of 1. Only one way to achieve that event. How about the probability of rolling a 5 or a 6? Probability of 5 or 6. Well, that's 2 numbers. And 6 in the sample space, right? It reduces to a third. That's 0.333, 33.3%. Okay. That's, the basics right there of basic probability. Now, as we go, we'll just get more advanced with asking probability questions. So let's go to the next page. On this one, find the probability of the event. Write the probabilities in the 3 ways. Okay, so this consists of rolling a 6-sided die and tossing a coin, right? So now we've got 2 objects. Let's say it's a fair die and a fair coin. So the die has 6 possible outcomes. The coin has 2. So if I wanted to find the sample space, I gotta list all the possible outcomes. For example, I could get a heads on the coin and a 1 on the die. A different outcome would be a heads on the coin and a 2 on the die, etc., right? So there's all these outcomes where I get heads and a different value on the die. And then I would do all of that with tails, right? Okay, so there's a way I can list all the outcomes. And now I've got them all, right? There's no other outcome when I roll those or toss those 2 objects. One of those 12 things is going to occur. And each one has the outcome of each of the objects in it, right? Like H1 has heads and a 1. Once we have that listed, it's going to be easier to find the probabilities because now I can count up the number of values in the sample space, which I see there are 12. So anytime I ask or answer a probability question, I know the bottom number is 12. What's the probability of rolling a 3 and tossing tails? That will be our T3. What's the probability of T3? Right? There's only one. Right? There's only one T3. There it is. So that's going to be a 1 out of 12, which is about 0.083 or 8.3%. Whoops. What did I do there? Okay. Is that event simple? Look at that numerator. Yep, it's 1. So yes, only one way to get T3. Only one outcome is that. It's the probability of rolling a number less than 4 and tossing heads. Okay, so let's see if we can count that up. Less than 4 and tossing heads. Let's see, that one, and that one, right? Those are all less than 4, not 4, but less than it, and they all have heads, so there's 3 of them. So when I write the probability, let's see, we could write probability of about less than 4 and heads. Do something like that. Again, it's just descriptive in the parentheses. So we counted it up, there's 3 out of 12, reduces it to 1/4, 0.25, 25%. Of course, that's not a simple event because there are 3 ways to get it, not 1. Okay. Let's finish off the page and then we'll take a little breather, continue with the next video. This one, probability experiment consists of tossing 2 coins at the same time. What's the sample space? So this one's a little tricky because we have 2 objects, but they're the same type of object. But think of it as maybe 2 different colored coins, like maybe you have a blue coin and a red coin, right? So let's say we have something like this scenario. blue coin and red coin. Okay, then what's my sample space? All right, so we could get heads on the blue and heads on the tail. That would look like H, H, right? Okay, or we could get heads on the blue and tails on the red. That would be H and then T. Or we could get tails on the blue coin and heads on the red. That would look like this. Now those two middle ones are often thought of as the same thing because it's just one head and one tail, right? But there's actually two ways that could occur because we have two different coins, right? So heads on the blue, tails on the red is different than tails on the blue and heads on the red. And then there's one more, which is both tails on red. Right? Okay, so hopefully the color coding helps a little bit in noting that there are four values in this sample space. Right? And one of those four things is going to happen. That's the key in getting the probabilities right, because now you'll get that bottom number correct, and then the top number is just counting up how many events match, or how many outcomes match the event. So for finding the probability of heads on both coins, that's the probability of HH. And I just look, there's only one, and there's four of them total. 1 out of 4, 0.25, 25%. How about the probability of getting exactly one tail? So probability of 1t, exactly 1, so not 2, not 0. So how many values in this sample space have only one t? It's just those middle two, the ht and the th. So there's two of them, and there's still 4 total. So that would be the answer for that one. And then how about at least one tail? Probability of at least one t. Right, how many amount of at least one? So that term at least one gets a little confuses people sometimes, but at least one is one or more, right? So for at least one, think one or more, right? In this case, that's either one tail or two tails. So look at all of them that have either one or two tails, and that's the last three, right? That's this one is at least one, at least one, at least one. The only one that doesn't qualify is the one with no tails. So this answer is going to be 3 out of 4. 75% of the time, that is what we would predict to happen. Okay. Now the interesting about that at least one thing, that's always true. At least one is actually the opposite of none. Notice there are 3 of them that have at least one, and the opposite of that has none, right? And that will always cover the entire sample space. At least one will be some of the objects, none will be the rest. They always add up to 100% of the sample space. Whew, okay, so there's a good little stopping point. Let's take a breather, and then we'll come back and get into some more complex probability. Hope everything's going well, and send me emails if you have any questions. All right, talk to you soon. Bye.